Good day, students, future viewers. This is Matthew William Scow, a lecturer at CPUT, academic and a researcher as well. And I'm just basically having an introduction to my channel here. And it's the Mech Marine Engineering channel. And what the purpose of this channel is basically to assist both mechanical marine engineering students at University of Technologies or UOTs in Africa. So my plan for the channel is basically to put up certain links to certain problems in our textbooks, basically like a tutor of some sort where certain problems will be solved. And then the second one is obviously to use certain parts of my curriculum, of which I teach as supplementary content. For instance, the first one today will be using a software, RLC Spice, for electrical circuit simulation. So yeah, so this is a basic introduction of my channel, and I'm just gonna essentially incorporate this the first part here. Just thought it's worth mentioning to have an introduction. Probably will have a better one in future, but I just thought I'll just initiate it, start it off immediately. Okay, so what I'm doing today, first thing was I'll obviously issue my students an assignment, and part of the assignment is to conduct a simulation using a program called RLC Spice. So obviously you guys are aware of the assignment, and I'll just do a tutorial on basically on how to use the software and how to get specific values on this particular circuit. Obviously you guys have some background here. My students who are actually going to view this, and I'm just going to use example number 3 exercise in your textbook, Electrical Technology 2 textbook. And I'm going to show you, I'm going to sketch the circuit, get the total current, get the voltage drop across various, well, in particular resistor, inductance, and capacitance. Yeah, but anyway, so let me just get to the actual question and then begin with the actual software. So what they're requesting here is that we've got a circuit which has a resistor, inductance, inductor, and a capacitance. A resistor of 17 ohms, an inductor of 85 millihenry, a capacitor of 85 microfarads, and it's supplied with a 380 volt 50 source AC current. What they want is a voltage drop across each component. Okay, so that's one of the things we're going to do. And prior to obtaining the voltage drop across the component, we're going to need the total current. And we're aware that in a series circuit, that the total current is the same through each one of those elements. So without further ado, let's get into the software. So I'll just have to now unshare this and then share the software. Just give me a moment. Share entire screen. I think that's what I got to choose. So I'm assuming you guys can see it. And let's begin on the question. So number 3 was a simple series circuit. So first thing you want to do is go File, then you go New, then you have your first circuit. So obviously I've started off, I showed you a basic tutorial in class, but this is now for an RLC circuit. And obviously in future I'll probably have more tutorials. But anyway, so how we typically start, we want to start with a voltage source. Right? So we click on that symbol over there, and it has different types of components. But obviously we want a voltage source. And then we have to choose voltage. There we go. Cool. So this is a voltage source, and what we do, we keep in Control and R, and when you do that, you're able to rotate the component. So it's obviously depending on how you're going to want So I mean, there's a positive and negative terminal. So you can have it either way, typically, obviously in horizontal fashion. Once you're done, you click escape, and yeah. So what I'm doing now, I'm just zooming a bit out. Next part is you're going to draw your wires or your conductors, and you click on that. Have another click, have another click, and another click. So basically, you click on the wire, and what you're doing is that every time you want to sketch the wire, you click. Every time you want to change the direction, you click again, and click again. And what's cool of this is that the software basically lines up where all the wires is for you, so you can actually see, you know, so that you don't actually miss particular points. So I'll stop till then, escape again. So there are three components: the resistor, the inductor, and the capacitor. Where are those components? Those components are here. That's a resistor, that's your capacitor, and that's your inductor. Cool. So let's just click on your resistor. Again, control, keep in control, then R, and when you press R, it rotates. Want it like that. Y again, click, and then escape. Then we add inductor, just shifting that around, click. We click again, the wire, click, and then escape, and then click again, then control R, and then line up and escape. Then we need to just close up this, because I mean, obviously the circuit needs to be closed so we're able to, obviously the current can run through the circuit. Cool. Next is to characterize our components. So we need to give it values, right? So, or give it properties rather, in this case. So for this question, we had a resistance of 17 ohms. Was it 7? No, sorry, this is number 3 in the textbook, right? Yeah, so it's 18 ohms. Cool. It's not, which question am I doing? I said number 3. Number 3 was number, let me just make sure I'm getting this right here. Number, just give me a moment. It's number 3, and cool. Just trying to get something right. Oh yeah, there we go. Number 3. So we have 17 ohms. Right click, 17 ohms. Right click. That was 85. So you just type in 85 and then an M and then a big H. Again, what's called Spice, it knows that that's 85 millihenry. It follows, you know, your standard notation of milli, micro, and so forth. And for your capacitance, you're going to have to go 85 mu F, and okay. That's basically done there. And then we have to characterize a voltage source. So what's important here is that we are running an AC circuit simulation. And what you're going to have to do now is click on advanced. And when you're on advanced, all you're going to have to do is include your voltage over here. In this case, it was 380. So don't worry about your frequency for now. We will get to that. And then lastly, we always need to ensure there's ground. And that's a form of protection, that we always ensure if there is a leakage in current, it'll run to the ground. And I think it's just good practice on any circuit in general. So I think they incorporated that within the software. Next step, we want to simulate. Click on simulate and click on edit simulation, CMD or command. So there's different types of simulation you can do. We've got a transient analysis or AC analysis, DC sweep, the noise, DC transfer, and a DC operation point. What we'll be doing is on the second tab, AC analysis. And yeah, so the first thing we do is click here, linear sweep. So type of sweep, we choose linear. We can find out on the LT Spice manual what this other types of sweeps mean. Number of points, we can say 100. It's basically, it's just to set up the graph. But in this case, it's not a big deal. We can say 100 over there. The frequency, so this is what's important. So this is your source frequency. So if it was 40 hertz, we put in a specific value. If it was 60, this is where you're going to want to put it in. So we're starting at 50 and we're ending in 50. And we could also, and I'll probably do it after this, is have a range of frequencies, and that is where you can actually find your resonant frequencies. So I'll probably do that as well. So click OK, and once that is done, you just click again, right click, and then we should be done. Then we go simulate, and then I think we can go edit there, and then we can just say OK again, just making sure. Then we can click run. As soon as you click run, you should get a list of values. Cool. So if I'm looking at this over here, I'll just plot this here. Our total current will be the same for each one, right? So it'll be 18.8944. And obviously, so we're looking at R1. That over there means that's a current going through there. If you look at L1, that will be the current going through there. And if you look at C1, you get the current going through there. And if we compare that to our total current in, well, I think that's exactly the same. Yeah. Cool. So that's 32. And what this value is just essentially 180 degrees out of phase compared to these values. But the magnitude is definitely correct with its corresponding phase angle. Next, the question was to find the voltage drop across the respective components. So if I revert back to the thing, we had the voltage drop across, I think that's the resistor, the inductor, and then the capacitor. And if you compare that with this, we get 3 different types of voltages here. So the first one is 380 at different, 3 different types of voltages. So let me try to explain what that is. First things first, we keep in control. I have control keeping, and we have to move. I'll need to move across with the mouse across each of these components, right? And you start over here. This is ground, so this is the reference point. This is where we measure voltage from. And as you move across to the next part over here, you find that this is called node 1. So what that is, so the voltage drop across here to here will be a particular voltage drop, and that'll be the V1 which you had in your in the answer window. And if you move across here, you'll get node 2, right? And if you move across there, you'll get node 3. And I think I didn't mention where it's this node, but it'll be at this corner over there. So I'll just do that again. From ground, that's node 1, that's node 2, and that's node 3. Okay, and then you'll notice over there, and then there's still node 3, and eventually ground. So how we actually do this is that to find the voltage drop across the particular component, you're going to have to say like node 1 minus ground. You're going to have to say node 2 minus node 1, and then node 3 minus node 2. And by then, so there's ground, node 1, oops, node 1, that's node 2. So basically we have to take the voltages they give us and subtract them from each other. So I'll just resimulate this and I get the value. So what you want to do is subtract these values. So obviously for node 1, I think we got our first voltage drop, and I think if you look at the answer there, it's 3 to 1. Well, obviously there's an angle difference there, but I think it's because, yeah, anyway, we'll get to that. And if you look at node 2, we've got 598, which doesn't look remotely the same, and node 3, it's not the same. So how do we get these values over here? The 504 and the 707. Cool, let's quickly see. So node 1 is still fine, but let's pull up a calculator and then keep that going. So let's do it over here. We got mode, number 2 complex, and for node 1, I just want to see something. Okay, so let's work at the voltage drop for node 1 is already given, is 3 to 1 at that phase angle. I'm just trying to figure out why it would be 180. That's probably to do with the way we structured the source. Possibly, but anyway, let's get back to the calculator. So we've got that. So if you want to find the voltage drop across the inductor now, we got to say node 2 minus node 1. So I'll type that in my calculator. So it's 598.125 at an angle of minus 90.1902 minus node 1, and node 1 is 321.205 at an angle shift at minus 147.0. That is a mistake on my end. I think I'll read this again now. So it's 598.125 shift at an angle of minus 90.1902 minus 321.205 and then shift at an angle of minus 147.707. Click equal. Then we go shift complex 3 equal, and we should get 504.55 minus at minus 57.729. Compare that to this, you get 504, and our angle is obviously 180 degrees out of phase in this case. So yeah, so that still kind of works out quite well. And then obviously this 180 degrees, you can see it's all due to this over here. So this is not actually at 0 degrees, which it should typically be. Hence, you'll find a 180 on each of these values. And if you want to find the voltage drop across the capacitor over here, we'll take node 3 minus node 2. So let's quickly do that. So node 3 would be 380, once again in an angle, shift angle 180. Oh, okay, that didn't work at all. 380 shift at 180 minus 598.125 shift that at minus 90.1902 equal shift to 3, get it into polar form. We get 707.526 and at an angle 122.29. And then checking the answers, 707, we get 706, what is it, 707.6, that's pretty spot on. And again, our angle is 180 degrees, so if you subtract 180 from 122, you'd actually get that 57 odd degrees. So that's how you find the magnitude. I think with the angles, it could be, we have to look at this. And I think if I characterize this, maybe the phase I should say 0 possibly, and let's try to simulate it again. Run. Okay, now it gives us the same answer.